Jai Hind. Myself Dr. Amita Asthana from Ajay Kumar Garg Engineering College. Here in this video lecture, we will study some operational amplifier concept. As we all know, the problems in the examination comes on Opamp, and the numericals can be solved with some easy tricks and easy techniques, and that we are going to explain in this video lecture, right? So here there are some concepts which we need to decide before proceeding through the numericals. So here we start. Concepts. Some concepts we need to describe first. Like, we will assume the Opamp that one input we are giving at this A terminal. This is A point. The voltage of this A point is VA. This is my B point, and the voltage of this potential of this B point is VB. Now here we will take the output or VO of the Opamp, the output terminal, right? This is inverting terminal and this is non-inverting terminal, right? Now, before proceeding towards the numerical, 2-3 things we have to ensure. What are those points? Number one, we will consider Opamp is ideal. Okay. Number one point is that we will consider Opamp to be operating in ideal mode. After that, in the second point, we will check before proceeding through the numericals that this feedback resistance to be connected through the inverting terminal of the Opamp, right? This feedback to be given at the inverting terminal of the Opamp, right? Next point. So RF at inverting or negative terminal. The second point we must note, right? If these two conditions have been satisfied, then there are few points that we have to apply. The virtual ground concept, of the Opamp, right? So here now what is that? First condition is Opamp is ideal. Second one is RF at negative terminal, and third condition is virtual ground concept. So before starting the numerical, we have to apply the virtual ground concept of the Opamp, right? So according to this concept, the A point potential VA is equal to the B point potential, that is VA is equal to VB. That means this terminal potential is equal to this terminal potential. Now, why this virtual ground concept applies in case of ideal Opamp? Because here, since the Opamp provides or gives infinite input impedance, and hence we consider that Due to the infinite input impedance, the current entering from inverting and non-inverting terminal of the op-amp is 0. So this is very important concept, that there is no current which is going to enter into the circuit of the op-amp. So here, if there is no current, then whatever current is coming from VA or A point, that will go directly to my feedback resistance. This is important. So we will apply these three concepts to solve our numericals. Like here. So first point is op-amp is ideal, second point is RF at negative terminal, and third point is VA is equal to VB, the VGC concept. So these 3 points, first of all, we will check, and then we will proceed for further solving of the numericals, right? Now next, let us take some small example, and then we will proceed in the same way. Only one technique is there that we will apply in this for all the numericals, and the numericals can be solved very easily, and that is nothing but the Kirchhoff current law, that is KCL. We will apply KCL and the all these 3 checkpoints, and then we will proceed towards the numericals. So here we go. Considering numerical number 1, through this numerical, we will understand the concept for the op-amp. Now in this numerical, we have to solve for the output voltage, that is VO is equal to infinity. We have to solve for the voltage VO is equal to what is the value for the output voltage. Okay, so here we will consider first of all the op-amp to be ideal, and then we will check whether this RF is given at the negative terminal or not. In this numerical, if we are checking, we can easily find out that RF is obviously at negative terminal. So this is my point B and this is my point A. This potential is VB and this potential is VA, right? Now both the conditions have been applied. The op-amp is ideal, and the second one is that the RF is connected to the negative terminal of the op-amp. Now I can easily calculate my output just by applying virtual ground concept and KCL. Only 2 things we need to apply. First is your virtual ground concept, and second one is KCL. Right, KCL is nothing but the Kirchhoff current law. Okay, so according to the VGC, if I think that VB is equal to 0, right? If my VB is equal to 0, then VA is equal to VB from VGC, and VA is also equal to 0. If this is equal to 0, then this is also equal to 0, right? This point voltage, the voltage of the node A, I am repeating, the voltage of node A is equal to 0 volts because VB is connected to ground. Since VB is equal to 0, by applying virtual ground concept, the voltage of A point is also 0. Because VB is 0. If this point is clear, then we will go to KCL, right? Now, how to apply the KCL? Let us apply KCL after this consideration, right? So applying KCL at A point. Okay. So the current from this I1, the current I2, here there is no current and that is equal to I. So I1 plus I2 to I, right? I1 plus I2 is equal to I. Then how I will calculate I1? I1 is nothing but, see, VA minus 0 upon R1. Okay. And I2 is VB minus 0 upon, this is, let's say, R2. Is equal to I. I is 0 minus VO upon RF. Okay. So VA minus 0 upon R1 plus VB minus 0 upon R2 is equal to 0 minus VO upon RF. Okay. So we have applied KCL at node A and see how I am moving from left to right to find out the current in the branches, right? So here that will be here. Now I will calculate for my VO. So minus VO upon RF is equal to VA upon R1 plus VB upon R2, or if I calculate for VO, that is equal to minus RF upon R1 into VA minus RF upon R2 into V. Okay. So this is my solution. I have calculated the output voltage very easily. So there is nothing very difficult in this, but very easily by applying only two concepts, VGC and KCL, we are able to solve the numeric, right? So this is how the Opamp is working, and we can calculate the numerical for Opamp, right? So this VA upon R1 plus VB upon R2 is equal to minus V upon RF, and here hence I have calculated. Now I repeat the process and say in the similar way we will do this. VA minus 0 upon R1 plus VB minus 0 upon R2 is equal to 0 minus VO upon RF. Only this particular step I did and I got the answer, right? Now let us take another example for the Opamp. Let's say any numerical can be solved using this. So here we go. Now I will take inputs at both the terminals of the Opamp. Five volt, Okay. 2 kilo ohms, 2 kilo ohms, 2 kilo ohms. 7 volts, 5 kilo ohm, 10 kilo ohm. Now the question is asking to calculate the output voltage, that is VO. Again, we are going to check two major points which are very important. That is, what is the Opamp consideration, whether it is ideal or practical. We will consider Opamp to work in ideal mode. Second, the RF, the feedback resistance, whether it is connected to the negative terminal of the Opamp or it connected at the positive terminal of the Opamp, and we can easily see the 10 kilo ohm resistance, which is a feedback resistance, and that is connected to the negative terminal of the Opamp. Here the RF is connected. Now, using virtual ground concept. Now I have to apply the virtual ground concept, right? If I want to apply my virtual ground concept, then I will calculate the potential at this point. This is very important. This is VB. The potential of this point is VB. This is A point. The potential of this point is VA. Right? This is VA. Now I want to calculate first the VB. I know from virtual ground concept that VA is equal to VB. But I don't have the value of VB. But some resistances are given at the non-inverting terminal and voltage sources are also there. So I can easily calculate the potential at V point, and that is nothing but the VB. Right. So here what I will do, first I will apply the KCL. From virtual ground concept I will write first. Virtual ground concept is VA is equal to VB. Now, first thing I have noted down, but I don't have the value of VB. So I will calculate VB applying KCL at point B. Why I am applying KCL at point B? Because I want to calculate the potential at B point, right? So here again this 5 minus VB upon 2 kilo ohm plus 5 minus VB upon 2 kilo ohms into 10 raised to the power 3 is this current is incoming is equal to this is equal to VB minus 0 upon 2 into 10 raised to the power 3. Simple KCL I have applied, nothing. Another thing, next thing I have did, that is only applying the KCL. I have applied simple KCL at B point, that is 5 minus VB upon 2 kilo ohm. 5 minus VB upon 2 kilo ohm is equal to VB minus 0 upon 2 kilo ohm, as I did before. Similar way, there is no other way. And now here all these 2 into 10 raised to the power 3 get cancelled, and 5 plus 5 is equal to 3 VB, and hence I can say that VB is equal to 10 by 3. So I have get the value of VB in the first step, that is VB is equal to 10 by 3 volts. If this VB is now known and that is equal to 10 by 3. Now from this virtual ground concept, I can write VA is equal to 10 by 3 volts. Now I will again apply KCL at A point, because where I have to go, I have to find out the voltage at output. Okay, for this output voltage, I have to apply KCL once more, but now at point A, right? So here, applying KCL in the next step we will do applying KCL at point. Now I have got the value of VB. Now once VB I have, then only I have to do one thing, and that is applying KCL at node A, right? So here I am applying KCL at point A. Okay. Now this A point, the voltage is VA. 7 minus, and that VA is nothing but 10 by 3. Okay. So 7 minus 10 by 3 upon 5 into 10 raised to the power 3. Okay. Is equal to, no other branch, is equal to VA minus VO upon 10. That is, VA is 10 by 3 minus VO upon 10 into 10 raised to the power 3. Now here, this will also cut by 2. Okay. So again solving this, 7 minus 70 minus 21. So we will solve it. 21 minus 10 upon 3 is equal to, and take this 2 here, okay, is equal to 10 upon 3 minus VO. Now minus VO is equal to that is 11, 22 upon 3, okay, and this will be minus 10 by 3. Now I will again solve. That will come out to be 12 by 3, and that is 4 minus VO. So VO will be equal to minus 4 volts. Check for the calculations, and hence we can calculate the output voltage at the OPAMP by using these 3 concepts for while we are solving the OPAMP numericals. Thank you. Jai Hind.